Hey yo, what's up? It's your boy Linford over here, talking to you about the algebra of complex numbers. In this video, we're going to be talking about how to add and subtract complex numbers, as well as how to multiply complex numbers. And as we look at how to multiply complex numbers, we're going to look at what happens when I have different powers of I that's thrown in there. As always, make sure to like, subscribe, drop a comment, ring the bell for notifications if you like this content. All right. First, talking about addition and subtraction of complex numbers. Here I have two complex numbers that we want to go and add together. Now remember, when we're talking about complex numbers, we're talking about numbers that can be written as the form a plus bi. And in this situation, this a is a real number, b is a real number, and I is the imaginary unit. Okay, so when we're talking about complex numbers and adding them together, we want to come up with a new complex number. So how do we do that? Well, a lot of people find this pretty obvious, but we're going to take a couple steps to kind of justify our answers. I don't really need to have the parentheses here, because this is all just addition. So I have 3 plus 4i plus 5 plus 2i. My stylus is kind of cutting out here, sorry about that. Now we're just adding things together, so I don't need to write the addition in here, or I don't need to write the parentheses in here since it's all just addition. And I'm going to use the associative property to say, you know what, why don't I just move some things around? So why don't I put the 3 and the 5 together, and the 4i and the 2i together? Okay. Obviously, the 3 and the 5 are going to make 8. But what do I do about the 4i and the 2i? Now remember, I, we're going to represent as a radical. Square root of negative 1. And I'm not being very super technical here, but we can think of this as I being the square root of negative 1. So, hey, what do you know? We have like radicals here. So we're just going to go ahead and add these together to get 6 root negative 1, or we could just write this as 8 plus 6i. Very straightforward process, super easy. All that we have to do, and if we were to write a process for this, we would just need to say for this process that we want to combine I guess we could call them the like terms. So go ahead and combine these like terms. Add the real parts together, and then add the imaginary complex parts together. And it's as easy as that. It's almost as if we had two binomials, right? If we had x plus 3 and x plus 5, something like that. Super straightforward and easy. Just remember, once you're done combining them, please write your answer as a plus bi. So just remember, we started off by adding two complex numbers. Our answer better still also be a complex number. So just go ahead and write it as that. Now, when we're talking about subtraction, subtraction works the exact same way, except we just have one little thing to adjust. So if I had the problem, let's say that I have 5 plus 2i, and instead of adding, I want to subtract the number 3 plus 4i. Whenever I'm working with complex numbers, I always write them in parentheses, because we want to remember that each of these individually are one number. So 5 plus 2i is one number. 3 plus 4i is one number. So we want to treat them as such. We just want to treat them as their individual numbers and recognize that. Now, if we're going to go ahead and subtract this, well, I can't just get rid of the parentheses yet. I'm going to have to distribute this through. So we're going to just say, well, that's 5 plus 2i minus 3 minus 4i, and we can rearrange some stuff. Why don't I group all the real components together, and then why don't I group the imaginary components together? Again, nothing too complicated. 5 minus 3 is 2. Positive 2i and negative 4 makes negative 2i. And we're done. That's it, really. Sometimes students go in, they might say, hey, Mr. Linford, look, there's a GCF of 2 in here, and do you want me to factor that out to write this? Nah, don't worry about doing that. I don't want us to go in factoring out complex numbers, because really, we're not trying to factor anything here. I'm just trying to look at what the resulting number is. What is the difference of these two numbers? Well, it's this number. Okay, so please don't worry about factoring stuff out. So if we were to look at this and come up with a process for how we went and subtracted these numbers, we would first start by saying you distribute the negative. And then we say, well, you just combine the like terms. Combine the like terms. You add the real parts, and then you add the imaginary parts together. You combine those just like we did before with addition. And please, for the final step, make sure your answer is written as A plus bi. Make sure your answer is still in that form for a complex number. Now that we have talked about how to add and subtract them, it's pretty straightforward. Why don't we take a couple minutes to pause the video, do some practice problems, then we'll come back to look at how to go ahead and multiply these complex numbers together. All right, well, hopefully you had a chance to pause the video, practice your skills with how to add and subtract. They're really not that bad. We just have to be careful with some of the signs that we're using. So why don't we take a look now at how we go about multiplying complex numbers. Now, complex numbers are, in a sense, two-dimensional. They have a real and an imaginary dimension, right? They have a real and imaginary component. So we can treat them very similar to how we treated polynomials or just general expressions. So if I had 2 plus 3i and 5 plus 3i, I'm going to think of this as 2 plus 3x times 5 plus 3x. And it's going to really behave the same way, because really, these numbers are two-dimensional, so we're going to start thinking of them as we almost have to perform this multiplication, we have to do that repeated distribution we've previously talked about. So we're going to take 2 plus 3i, and I'm going to distribute this through the second number. I'm not going to call it a binomial because it's not really a binomial, it's a number. So if I distribute that through, we end up with 5 times 2 plus 3i, and then we end up with 3i times 2 plus 3i. See how we just went through and distributed the 2 plus 3i? And then when we're done with that, we realize, okay, well, we're going to have to distribute again. So we end up with 10 plus 15i plus 6i plus 9i squared. All right, so let me rewrite this kind of like how I would write a polynomial. We have 9i squared plus 6i. Oh, actually, we can combine that with the 15i, my bad, to get a 21i plus 10. Okay, this isn't too bad. But this is kind of a little different. I typically want my answers written as a plus bi. I want a complex number, but I don't have a complex number here. That's not really met because I have this weird thing with a 9i squared. So we're starting to think, well, maybe if we multiply two complex numbers, we don't get a complex number back. Well, that's not really the case. We should get a complex number back. So maybe there's something we could do to this expression to realize that maybe we can simplify it down or rewrite it in a different way. Well, before we do that, we want to recognize what is this I squared business, and maybe it'll help us to start thinking of this problem in a different way. Remember, I is the square root of -1. Again, not being super technical here. Really, the definition says that I squared is equal to -1, but we're going to write this. So by the definition, we have, like I just said, I squared equals, well, we have -1 squared, which is just -1. Okay, so maybe we realize, hey, we just have a -1 in there. That's not so bad. But now I'm starting to wonder, what are some other powers of I? What happens if I take I cubed? Well, that was I squared, which was -1, times I, which is I to the -1. So we get negative root -1, which is -I. Does that make sense? Think about it maybe a little more drawn out and elaborate. For I cubed, I was just saying that we have I times I times I, which is just root -1 times root -1 times root -1. Well, these together make -1. This one doesn't really simplify, and so we end up with negative root -1, root -1, my bad. And that's just -I. So if I took I cubed, I just end up with -I. So what I'm doing here is I'm just tacking on an additional root -1. So let's clear some space. And let's see what happens if I have I to the 4th. So if I took I to the 4th power, all right, that was I to the 3rd, which we said is -I. And then we're also going to tack on an additional root -1. Okay, so let's see what we get here. Isn't that just, well, that's -I. -1, root -1 here is just I. So I have I times I, that's I squared, so -I squared, and that's just going to be -1, which results to +1. Okay, maybe getting a little more elaborate in here. Let's see if I have some extra paper to work with. I was just asking, what's I to the 4th power? Well, that's I times I times I times I. Okay. I know that I times I is going to be -1, and I know I times I is going to be -1. So altogether, they should give me +1. If you wanted to see it a little more drawn out, you could do root -1 times root -1 times root -1 times root -1. And you could see kind of how that whole process gets a little more elaborate. Now, that's fine, and I could just keep doing this. And I'm kind of curious what happens here. Because if you'll notice, from where we went, we started with what we defined I as, and then we jumped down to I cubed being -I. We jumped to I to the 4th being +1. I wonder what I to the 5th is. Let's see, I to the 5th. We have I times I times I times I times I. Yeah, there's easier ways of doing this than just writing out an expanded form, but I think this is the most obvious to see. All right, I times I. Well, that's just -1. And again, I have I times I, that's just -1. But then this one that's kind of all by itself, that's just the standalone square root of -1. All right, so let's see what we have here. -1 times -1 is +1. +1 times root -1, huh? So we have +1 times the square root of -1. Well, that's just the square root of -1, which is just I? Yeah, it looks like. So it seems that if I have I to the 5th, I end up with I again. Wait a minute, didn't I already see that before? Huh. Let's start getting a table of these values and see how we might start noticing if there's any pattern that's popping up. So we had I to the 1st was just equal, well, to I, of course. Then I had I to the 2nd power, that's equal to -1. I to the 3rd power, we said is equal to -I. I to the 4th power, well, that was equal to +1. And then we had I to the 5th, and we just said that was equal to I again. All right, let's look at I to the 6th power. Again, there's probably a better way of doing this. Well, there are some easier way, or I should say some quicker ways to go about doing this than just writing expanded form, but just for the sake of the lesson, let's go ahead and write this in expanded form. We'll notice that I times I here is -1, I times I here is -1, I times I is -1. So I have -1 cubed. So that's -1 times -1 is +1. Times -1 is going to be -1. So I to the 6th equals -1. Let's keep going. I'm curious what happens at some of these higher powers because I'm starting to notice, if you look at that table, we're starting to notice that there are some things in common that keeps popping up. And we're going to be wanting to work with higher orders of I. So knowing what this potential pattern might be a little helpful. Let's take I to the 7th, and you know what? Let's go ahead and maybe try an easier way of doing this as opposed to writing it in expanded form. I to the 7th is just I to the 6th times I to the 1st. Well, I to the 6th, we just said, hey, that's -1. And I to the 1st, we said, is just I. So I to the 7th should just be -1 times I, which is -I. There we go. And then just for kicks, let's go ahead and do I to the 8th. All right, using this technique, that's just I to the 7th times I to the 1st. I to the 7th we just said is -I, and I to the 1st is just regular I. Oh boy. So let's see. I times I is going to be a -1. So I have -1, which results in a +1. So I to the 8th equals +1. You should notice that there's a bit of a pattern going on here. Really, when working with I is going to be what I'm going to reference as cyclic. It performs like a cycle. And it does so around the 4th exponent. So what happens here is in groups of 4, I follows this pattern. It goes from I to -1 to -I to 1 and back again. It keeps repeating this pattern, and it does so every 4 exponents. You'll notice that I to the 4th is equal to 1 and I to the 8th is equal to 1. So every 4 exponents, you'll always get back to the same value. So just for practice sake, let's say we had I to the, let's say we had I to the 24th power. Do I really want to write out 24 i's See how many are grouped together? No, of course not. Now I can think, if this pattern continues, I went from I to the 8th is going to be 1. So starting at I to the 4th is 1, then I to the 8th, then I to the 12th, I to the 16th, and then going from there, I to the 20th, and then I to the 24th. All of those numbers we just listed off, I to the 4th, I to the 8th, I to the 12th, I to the 16th, I to the 20, and I to the 24. All of those numbers will be in the same order of the sequence, so they will all have the same value. So I to the 24th should be 1. And then if I took I to the, let's say, 33rd power, well, let's think. What's the closest multiple of 4 to that? Well, I know that I to the 32nd, 32 is a multiple of 4, so that should be a 1. So what we have going on here is we just took I to the 32 times an I to the 1st. Okay, so we ended up at the end of our cycle, so we must go right back to the start. So this better just be an I. Hopefully you're starting to see that this cycle just keeps popping up. If you're trying to figure out what the value of I to some exponent is, just ask yourself, where's the nearest multiple of 4? Then count up from the cycle. If you said the nearest multiple of 4 is 2 less than where I'm at, then your answer is going to be -1. If you're saying the nearest multiple of 4 is 1 below where I'm at, then you're 1 in the cycle. And you can use this method because of this, what I'm going to call cyclic nature with I. It keeps repeating this pattern again and again and again. Okay? So let's take our knowledge now of higher orders of I and let's apply it to simplify this problem. Well, we said we have 9, and instead of I squared, we know that I squared is really just -1. So we've gone back from imaginary, purely imaginary, to now real numbers. So that's just going to be -9 plus 10 plus 21i. So -9 plus 10 is a 1 plus 21i, and we're done. That's how we go ahead and solve this problem. Now, yes, we did some long, drawn-out multiples distribution, but really, any type of multiplication that we had when we were multiplying polynomials together will go ahead and work here. You could have foiled this problem. You could have done box method with this problem. But ultimately, when we're done, we're going to have to, have this understanding of what I squared is to do some simplifying to get our number to be a complex number. It's very important that every time we add, subtract, and multiply these things, our answers stay as complex numbers. So if we're going to go ahead and think of a process to this, let's go ahead and write down some of what we might do. So first we might say that we are going to multiply the numbers, and we could say using FOIL, we could say box method, or we could say distribution. Really, FOIL and box method are just a type of distribution. But go ahead and multiply the complex numbers. Simplify I squared to be -1. you pretty much always will have an I squared in here. Because if you think back to when we were multiplying just regular binomials, we would end up with an x squared. So the same idea is going to apply here. We should probably end up with an I squared. So just remember to simplify I squared to be -1. And then go in and simplify the number to be in the form a plus bi. That's what we want our final answer to be in, so make sure that we just simplify it to get like that. Okay, now that we got some of this idea in our head, let's take a couple minutes, go ahead and practice through some of the problems. I would like to pause the video right now, give you a chance to practice these problems individually, see where you're at level-wise with this, and then we'll come back and check our answers. All right, well, hopefully you're able to pause the video, but if you just have to skip forward to just see the answers, that's totally fine. I'm going to try to move through these a bit quicker. So if I'm going ahead and adding complex numbers, again, just combine the like terms. I'm going to combine the real parts of 4 and 2. If my stylus ever works. Okay, 4 and 2 combines together to be 6, and then -3 and 6 combine together to be +3i. So then we're going to go and say, well, I got some subtraction, got to distribute this through. We have 7 plus 10i minus 3 plus 5i. All right, well, I'm going to combine the real parts. 7 and -3 make 4. 10i and +5i make for 15i. So I have 4 plus 15i. Now, addition and subtraction are not that bad. So when it comes to multiplication, again, not that bad. Find what method you like. I like box method just because I like how it organizes my work, and I find it fairly quick and easy to use and interpret. So I make the box. I'm going to go ahead and multiply the columns and rows. This becomes a 6. That's a -16i. That's a 15i. And then we're going to end up with -40i squared. Okay, let's write down what our answers are going to be. Well, obviously we have some like terms here. So we have a -40i squared. Let's combine the -16 and the 15 to make -1i plus 6. But remember, this is not in the form we want. So we're going to take -40i squared and recognize that's -40 times -1. And then that's just going to be +40 minus I plus 6. So combine those real parts and we get 46 minus 1i. All right, hopefully this is starting to make a bit more sense. Let's go through the next one. Number 4 is going to be also done by box method. Let's do -3 and the 5i. Let's do the 7 and the -4i. We get a -21, a 35i, a 12i, and a -20i squared. All right. Before we even start writing this out, let me go ahead and simplify this right now. -20i squared should just be +20. Okay, so I know right away I can change this around. So let's go ahead and start writing what we have, and of course we notice that there are like numbers on the radical, or like terms on the radical. Oh my gosh, on the diagonal. This is what happens when you're just making these YouTube videos at like 3 a.m. and you haven't had that much coffee. Okay, so let's go ahead and combine some like terms here. I'm going to start with the real numbers. We got 21 and 20, or I should say -21 and 20. That gives me a -1. And then we have 12i and 35i. That should be 47i. And that looks like it should be good enough for us because we get the negative 21 and the positive 20. That gets us that negative 1. And then we have the 15i and the 12i. Oh gosh, it's really late. Let me think. The 35 and the 12i. So 35 plus 2 is 37 plus another 10. Yeah, that's 47i. And it's written as a complex number. So there we go. That's our answer. All right, let's finish strong with this rather unusual one. But remember, this is totally allowable. When we defined complex numbers as being of the form a plus bi, we said that a and b are just real numbers. So we said that they don't have to necessarily be whole numbers. I'd like it if they were whole numbers, right? That would make my life much easier, but they don't have to be. They could be fractions. They could be irrational, like the square root of 2 or the square root of 8. They could be pi. So just be comfortable working with some more unusual types of entries. But box method will be good for us just the same. Root 8 and I, and then let's do root 2 and 4i. All right, root 2 times root 8 is root 16. I'm using that property of multiplication, where that says when I'm multiplying the same radical together, or I should say the same index together, I can multiply the radicands. Then we have I times root 2. We have 4i times root 8. And then we have 4i squared. All right. Before we start combining some stuff, maybe we should note 4i squared is just negative 4. And then, of course, the square root of 16 is just going to be 4. Again, I'm only taking the principal root here, just working with the positive. All right, so let's go ahead and jot down what we have here. We have 4 minus 4 plus 4i root 8 plus I root 2. Well, obviously, the 4's are going to cancel out. So our real part is going to be a 0. But then, what about our complex part? It's kind of difficult to see. Well, let's try to break down this root 8. Let's see if it breaks down into something that becomes a like radical that we can add together. So the square root of 8, I'm going to do this on the side here, is the square root of 4 times the square root of 2. Square root of 4 is 2. Hey, what do you know? The square root of 8 is just 2 root 2. So let's plug that in. So I have 4i times 2 root 2, and then I'm adding together another I root 2. So let's see, that's 0 plus 8i root 2 plus I root 2. So that should be 0 plus 9i root 2. You'll notice in this problem, something a little unusual happened. The real number part is just 0, and that's fine. It could be 0. We're not restricted on that. I never said that you can't have 0. In fact, 0 is a real number, so you should sometimes be able to have one of these be 0. So this number is what we're going to call purely imaginary or purely complex. It has no real number component to it. But the big idea here is that we're trying to combine, hey, remember your techniques with like radicals, and maybe we can go ahead and simplify this down a little further. I would still like your answer written as 0 plus 9i root 2. I don't want you to ignore this 0. Don't ignore the 0. Make sure to include it, because this says, hey, I still have a complex number, but I definitely know that its real part is going to be 0. It doesn't have a real part. This helps me when graphing, and this helps me when interpreting the situation, okay? All right, well, hopefully you found this video helpful and informative on how to do some algebra on the complex number system. As always, if you have any questions, make sure to email me at Linford, that's KLINFORD, at wccnet.edu. Feel free to email me with your questions, comments, concerns, telling me how awesome the video is, whatever you think. As always, make sure to like, subscribe, drop that comment if you like this type of content. And as always, hashtag Wrath of Khan, taking them down one video at a time. Hashtag Linford for life. I'll see y'all later.